master student at Faculty for Information Technologies. Also, I'm working at the bank as a software application specialist for 15 years. I will present you a study of comparing quantum software development kits for introductory level education. And Abu is my mentor for my master thesis. We focus on Qiskit, Cirq, and Forest, the quantum software development kits created and supported by IBM, Google, and the Rigetti respectively, and ProjectQ, an academic project, but still having direct industrial support as Huawei. For comparison, we define 6 tasks based on QWorld introductory tutorial called Bronze. Bronze was designed particularly for introductory level education. Up to date, it has been used to organize more than 16 workshops, online and on-site. Also, Bronze uses gate-based quantum programs. One advantage of gate-based models these days is their compatibility with the existing quantum computers using superconduction technologies developed by the well-known manufacturers such as IBM, Google, or Rigetti. Here is a list of subtasks of functionality we checked in each quantum software development kit. First, randomly generating very simple quantum circuit using classical conditional and loops, executing quantum circuit and reading the measurement results, visualizing the quantum circuit, simplifying the design by using classical subroutines, reading the quantum state and unitary operator of the circuit, implementing intermediate measurements, applying classically controlled quantum operators, and implementing quantum teleportation as a sophisticated protocol for the introductory level. To implement our tasks, we use Jupyter notebooks, and so we install Anaconda as it comes with widely used Python libraries, and so we do not need to install extra packages. This is the version which we used. The quantum programming libraries are written in Python, and their installation are easily done by this command. As you can see, there is one issue with Forest, bringing extra difficulties for the new learners. It has separated tools for complying and executing the quantum programs to be more efficient. But their installation should be done separately, and each of these tools should be started separately on command line in parallel to coding quantum programs in Python. So we suggest that Forest may have Python modules of these tools behind the external one. Here is task 1. This task is to design a quantum circuit with 8 qubits. For each qubit, we apply a NOT gate with half probability. Then we measure all qubits. This is a very basic example to use classical loops and conditionals when designing the quantum circuit. And subtasks are design the circuit, draw the circuit, read the results, and as a binary number. You can see solution in Qiskit for those tasks. Here is a solution in Cirq, and a solution in Forest, and a solution in ProjectQ. In task 1 is done in each quantum software development kit without any problem. Task 2 is to write a model function, return a quantum circuit to implement superdense coding protocol, where the classical message is passed by the user. Superdense coding is one of the basic quantum protocols using quantum entanglement. So here we use a very basic form of classical model programming. And our subtasks are for each classical message, 00, 01, 10, and 11, to design the circuit, draw the circuit, read the classical message. And we can see a code and solution completely. Also in Cirq, in Forest, and in ProjectQ, and taskbar is also done in each quantum software development kits. Our third task is to design a quantum circuit with a single qubit, apply a Hadamard operator, and measure the qubit. If the outcome is null, then apply Hadamard operator, measurement the qubit, and this is a very simple example by using intermediate measurement. And subtasks are design the circuit, draw the circuit, execute the quantum programs 1,000 times, and check the statistics. Here is solution in Qiskit. Cirq doesn't support to store intermediate measurement classically, which can be used later to apply certain quantum operator. And here is a solution in Forest. It uses LaTeX solution, which does not work in this task and task 5. And we have an error after execution command display that it is not supported. Here is a solution in ProjectQ. There is no output, a series of quantum circuit inside a loop. So at the end, we got a error message that we can't draw the circuit. Next task is to design a quantum circuit with 3 qubits. Rotate each qubit with angles, and then apply following control not operator. So a subtask was read the state vector, read the probability of being in each basis state, read unitary matrix, and measure all qubits. Second subtask are draw the circuit, execute the quantum program 1,000 times, and check the statistics. For 4, 5, and 6 tasks, we will show solution only in some libraries, not all. The code for every task are shown in GitLab repo, which is available now. And ProjectQ doesn't support to print the unitary matrix of a circuit, so we can't see that in a solution. Here we can see solution in Cirq. The next task is quantum teleportation. And the task is to design a quantum circuit implementing quantum teleportation, including the post-measurement parts. Subtasks are draw the circuit, read the measurement results, read the quantum states. This is a representative example for applying classical controlled quantum operator, and we can see solution in Qiskit here. And for the end, task 6, for given 4 angles, the first task is to design a quantum circuit implementing the unitary matrix. This unitary matrix, and where 0 is 2 by 2 dimensional 0 matrix, and R theta is rotation matrix with angle theta. to verify the correctness of the circuit, we will read the unitary matrix, and then we will the second task is to design a circuit applying 3 times and 5 times. To verify the correctness, we will read the unitary matrix. And in GitLab repo, there are 3 versions for solution for these tasks in each of the libraries, except it in ProjectQ, because it doesn't support to print unitary matrix. And this is just one solution. Here we are. This is second subtask, a solution for second subtasks. That's all. Thank you for your attention.
Thank you very much, Marija, for your presentation. I hope all these programs are available on GitLab.
Yes, it is available.
So yes, so because some people would like to see them. So please share your slides as well, and let's see if somebody has comes up with some questions. So you have some nice presentation remarks. So it was indeed very detailed, and
I will share my presentation.
Right.
And the link for GitLab.
Okay.
Awesome.
So I think there's no questions right now. So you can ask the question. So there's one question that has come up. If you like to answer, is it software study only, or is there any hardware connection with your study?
Could you ask again, please?
He's asking that what you have done is software, that is, you have developed the programs, or you can implement it on the hardware somewhere as well.
It is program which I test on my computer for simulation just.